Welcome to Napz, where knowledge and rest come together in perfect harmony. I'm so glad you're here with us today. Before we begin, take a moment to get comfortable. Adjust your pillows, pull up your blanket, and let your body sink into whatever surface supports you. There's nowhere you need to be, nothing you need to do. This time is yours. Today, we're going on a gentle journey through 100 facts about gravity, the invisible force that holds our world together and shapes the entire cosmos. You don't need to remember everything you hear. In fact, you don't need to remember anything at all. Just let the words wash over you like waves, carrying you deeper into relaxation with each passing moment. If you drift off to sleep before we reach the end, that's exactly what this is for. And if you find yourself still awake at the conclusion, you'll have traveled through some of the most beautiful ideas humanity has ever discovered about our universe. So close your eyes if you'd like, slow your breathing, and let's begin our exploration of gravity together. Close your eyes for a moment and feel the weight of your body against whatever surface supports you. That sensation, that gentle but constant pull, is gravity speaking to you. It's been there since the moment you were born, and it will remain with you for every breath you take. Gravity is the quiet architect of our universe, and today we're going to explore its mysteries together. Let's begin with something remarkable. Every single object in the universe attracts every other object. Right now, you are pulling on the moon, and the moon is pulling on you. The pull is unimaginably small because of your tiny mass compared to celestial bodies, but it exists nonetheless. This is the essence of gravity. It's universal, affecting everything that has mass. The force of gravity on Earth gives you your weight, but here's something fascinating. Your mass never changes wherever you go in the universe. If you have a mass of 70 kilograms on Earth, you'll have that same mass on the moon, on Mars, or floating in the depths of space. But your weight, the force that gravity exerts on that mass, that changes dramatically depending on where you are. On the moon, you'd weigh only about 1/6 of what you weigh on Earth. Imagine that for a moment. If you weigh 150 pounds here, you'd weigh just 25 pounds there. You could jump 6 times higher, move with an effortless grace. This isn't because you've changed, but because the moon has much less mass than Earth, and therefore exerts a weaker gravitational pull. We measure gravitational acceleration on Earth at approximately 9.8 meters per second squared. What does this mean? It means that if you drop something, it speeds up as it falls, gaining about 9.8 meters per second of velocity for every second it's falling. Drop a stone from your hand, and after 1 second, it's moving at 9.8 meters per second. After 2 seconds, 19.6 meters per second. The acceleration is constant, relentless, beautiful in its consistency. Here's where things get truly poetic. Gravity doesn't just pull things down, it holds entire worlds together. Our planet Earth, this sphere of rock and water and life, is held in its spherical shape by gravity. The immense gravitational force pulls all of Earth's mass toward its center, creating the round form we know. Without gravity, our world would simply drift apart, a cloud of disconnected particles floating in the void. And consider this. Gravity is why we have an atmosphere to breathe. The air around you, the oxygen filling your lungs right now, is held close to Earth's surface by gravitational attraction. Without it, our atmosphere would escape into space, molecule by molecule, leaving Earth as barren as the moon. Gravity is, quite literally, why you can take your next breath. The strength of gravity depends on two things, and two things only: mass and distance. The more massive an object, the stronger its gravitational pull. Earth pulls on you more strongly than the moon does because Earth has more mass. But distance matters too, and in a very specific way. If you double your distance from an object's center, the gravitational force doesn't just halve, it becomes 1/4 as strong. Triple the distance, and the force drops to 1/9. This is called the inverse square law, and it governs how gravity weakens across the cosmos. Perhaps most wonderfully, gravity acts instantaneously on all parts of an object equally. When you jump, every atom in your body feels the same downward acceleration. Your heart, your bones, your thoughts, all pulled by the same gentle, constant force. This is why falling, when there's no air resistance, feels like floating. It's why astronauts in orbit experience weightlessness, even though Earth's gravity is still pulling them strongly. They're falling constantly, in perfect harmony with their spacecraft, and so they feel no force at all. These are just the first whispers of gravity's story, the opening notes of a cosmic symphony that has been playing since the universe began. As we continue, we'll discover how this force shapes stars, bends light, and weaves the very fabric of space-time itself. Let's travel back in time now to a moment that changed everything. In 1687, Isaac Newton published his law of universal gravitation, giving humanity its first mathematical description of this invisible force. But the story begins earlier, with an apple orchard and a contemplative mind. Whether or not an apple actually fell on Newton's head is debated, but what matters is this. Newton realized that the same force pulling fruit to the ground was the force holding the moon in orbit around Earth. The heavens and Earth obeyed the same rules. This was revolutionary. Newton's equation was elegant in its simplicity. The gravitational force between two objects equals the gravitational constant multiplied by the product of their masses, divided by the square of the distance between them. Written as F equals G times m1 times in m2 divided by r squared. This formula could predict the motion of planets, the trajectory of comets, the rise and fall of tides. For over 2 centuries, it seemed complete. But here's something remarkable about Newton's gravitational constant, that G in the equation. It's one of the most precisely measured numbers in all of physics, yet also one of the most difficult to measure. Its value is approximately 6.674 times 10 to the negative 11th power, in units of cubic meters per kilogram per second squared. This incredibly small number reveals something profound. Gravity is actually the weakest of the 4 fundamental forces in nature. The electromagnetic force, for comparison, is about 10 to the 36 power times stronger. Think about that weakness for a moment. A small refrigerator magnet can overcome the gravitational pull of the entire Earth when it holds a paperclip against a refrigerator door. The electromagnetic force in that tiny magnet defeats the gravity of a planet with a mass of nearly 6 trillion kilograms. Yet gravity dominates the universe. Why? Because gravity is always attractive. It works over infinite distances. And most importantly, it adds up. The more mass you have, the more gravity accumulates. This brings us to something both simple and profound. Galileo discovered it centuries ago, and it still surprises people today. In a vacuum, where there's no air resistance, all objects fall at the same rate regardless of their mass. Drop a feather and a hammer on the moon, and they'll hit the ground at exactly the same moment. Apollo 15, astronaut David Scott actually performed this experiment in 1971, and millions watched as feather and hammer fell together in the moon's airless environment. It confirmed what Galileo had argued against centuries of belief. Mass doesn't affect the rate of free fall. Now let's consider something that governs much of our daily experience: terminal velocity. When you fall through air on Earth, you accelerate downward due to gravity, but air resistance pushes back against you. The faster you fall, the stronger that air resistance becomes, until it exactly equals the pull of gravity. At that point, you stop accelerating and fall at a constant speed. For a skydiver in spread eagle position, terminal velocity is about 120 miles per hour. Change your position to a headfirst dive, and you can reach 200 miles per hour. This is why skydivers can control their fall by changing their body position. Gravity also explains why our planet bulges slightly at the equator. Earth isn't a perfect sphere. It's an oblate spheroid. The equatorial diameter is about 43 kilometers larger than the polar diameter. This happens because Earth rotates, and that rotation creates a centrifugal effect that works against gravity at the equator. The combination of Earth's rotation and gravity has shaped our planet into this slightly flattened form over billions of years. Here's something beautiful to contemplate: the center of gravity, also called the center of mass. Every object, no matter how irregular its shape, has a point where all of its mass can be considered to be concentrated for gravitational purposes. For a sphere like Earth, it's right at the geometric center. For your body standing upright, it's somewhere around your navel. When you balance on one foot, you're unconsciously shifting your center of mass to stay over your point of support. This principle governs everything from how birds fly to how skyscrapers stand. And consider the tides, those rhythmic rises and falls of ocean waters that have marked time for countless generations. They're caused by the gravitational pull of the moon and, to a lesser extent, the sun. The moon's gravity pulls on Earth's oceans, creating a bulge of water on the side facing the moon, and interestingly, another bulge on the opposite side. As Earth rotates through these bulges, we experience the high and low tides. In most places, there are 2 high tides and 2 low tides each day, a constant reminder of gravity's reach across space. These truths about gravity, discovered through centuries of observation and thought, paint a picture of a universe bound together by invisible threads of attraction. But our understanding was about to transform once more, in ways that Newton could never have imagined. In 1915, Albert Einstein published his general theory of relativity, and with it, he fundamentally reimagined what gravity is. Newton had described how gravity behaves, but Einstein explained what gravity truly is. In his vision, gravity isn't a force at all. It's the curvature of space-time itself. Massive objects like stars and planets create curves, dips, and valleys in the fabric of space and time, and other objects simply follow the curved paths through this warp geometry. Imagine placing a bowling ball on a stretched rubber sheet. It creates a depression, and if you roll a marble nearby, it will curve toward the bowling ball, not because of a force pulling it, but because it's following the curved surface. This radical idea led to predictions that seemed impossible, yet turned out to be true. Einstein predicted that gravity could bend light itself. In 1919, during a solar eclipse, astronomers observed stars whose light passed near the sun. The positions of these stars appeared shifted from where they should have been. Their light had been bent by the sun's gravitational field, following the curves in space-time. It was exactly as Einstein had calculated. The universe had confirmed that mass bends the very fabric of reality. General relativity also predicted something called gravitational time dilation. Time itself moves at different rates depending on the strength of gravity. The stronger the gravitational field, the slower time passes. This isn't metaphorical, it's measurable and real. A clock at sea level runs slightly slower than a clock on a mountaintop because it's deeper in Earth's gravitational well. The difference is tiny, mere nanoseconds per day. But it's real enough that GPS satellites must account for it. Without corrections for gravitational time dilation, GPS systems would accumulate errors of several kilometers per day. Here's something that captures the imagination: gravitational waves. Einstein predicted these in 1916, though he doubted they could ever be detected. When massive objects accelerate through space, like two black holes spiraling into each other, they create ripples in space-time itself, spreading outward at the speed of light like waves on a pond. For a century, these remained theoretical. Then, on September 14th, 2015, the LIGO detectors felt a whisper from across the universe. Two black holes, each about 30 times the mass of our Sun, had collided 1.3 billion light years away, and the gravitational waves from that ancient collision finally reached Earth. Humanity had detected ripples in the fabric of space-time itself. Let's turn our attention to something closer to home, but equally fascinating: microgravity. Astronauts orbiting Earth aren't actually in zero gravity. Earth's gravitational pull at the altitude of the International Space Station is still about 90% as strong as it is on the surface. So why do they float? Because they're in continuous free fall. The station and everything in it are falling around Earth at just the right speed that their curved path matches the curve of Earth itself. They never get closer to Earth, but they never stop falling either. This is what orbit truly is: falling sideways so fast that you keep missing the ground. Living in microgravity transforms the human body in profound ways. Without gravity's constant pull, astronauts' bones lose density at a rate of about 1 to 2% per month. Their muscles atrophy, particularly in the legs and back, the muscles that normally fight against gravity all day. Fluids shift toward the head, causing that puffy-faced appearance astronauts get in space. The spine elongates, making astronauts slightly taller. Some have grown by as much as 3 inches during long-duration space flights, though they return to normal height after coming home. Now consider escape velocity, the speed needed to break free from a celestial body's gravitational pull completely. For Earth, that velocity is about 11.2 kilometers per second, or roughly 25,000 miles per hour. Launch anything at that speed or faster, and it will escape Earth's gravity and never fall back. The Moon's escape velocity is much lower, only 2.4 kilometers per second, which is why the Apollo astronauts needed much less fuel to leave the Moon than to leave Earth. Every world has its own escape velocity, determined by its mass and radius. Here's a thought that bridges the cosmic and the intimate. Every atom in your body was forged in the heart of a star, held together by gravity during its violent death, and scattered across space to eventually become part of you. Stars form when clouds of gas collapse under their own gravity, growing denser and hotter until nuclear fusion ignites in their cores. Gravity compresses these stellar furnaces so intensely that hydrogen atoms fuse into helium, releasing the light and heat that makes stars shine. When massive stars die, gravity crushes their cores while blasting their outer layers into space. And from that stellar debris, new worlds and new life eventually emerge. And speaking of stars, our own sun's gravity extends far beyond what you might imagine. The sun's gravitational influence reaches out to define the boundary of our solar system, a region called the Oort cloud, which lies nearly a light year away. Every comet, every distant icy world in that remote realm still feels the sun's pull and remains bound to our star. Gravity is patient, holding its children close across distances that light takes months to cross. The deeper we look into gravity's nature, the more we find it woven into every aspect of existence, from the quantum foam of reality to the largest structures in the cosmos. Let's journey now to the most extreme manifestations of gravity in our universe. Black holes represent gravity taken to its ultimate conclusion, regions where space-time is curved so severely that nothing, not even light, can escape once it crosses a boundary called the event horizon. The term black hole was coined by physicist John Wheeler in 1967, though the concept dates back further. These cosmic voids aren't actually holes at all, but rather objects so dense that their escape velocity exceeds the speed of light. At the event horizon, time itself appears to stop from the perspective of a distant observer, a profound consequence of gravitational time dilation taken to its extreme. The density required to create a black hole is almost incomprehensible. If you could compress Earth down to the size of a marble, about 9 millimeters across, it would become a black hole. That's how tightly matter must be packed for gravity to become inescapable. For our sun to become a black hole, it would need to be compressed to a sphere just 3 kilometers in radius. The universe doesn't compress objects arbitrarily. Black holes form when massive stars, at least 20 to 25 times the mass of our sun, exhaust their fuel and collapse catastrophically in supernova explosions. At the very center of our own Milky Way galaxy lies a supermassive black hole called Sagittarius A star. It contains approximately 4 million times the mass of our sun, yet it's remarkably compact. This monster sits about 26,000 light years from Earth, and its gravity orchestrates the motion of billions of stars in our galaxy's core. We've observed stars orbiting this invisible giant at speeds exceeding 5,000 kilometers per second, more than 1% the speed of light. These stellar orbits provided some of the most convincing evidence that supermassive black holes truly exist. Now consider something gentler but equally important: Lagrange points. These are special positions in space where the gravitational forces of two large bodies, like the Earth and Sun, combine with the centrifugal force of orbital motion to create points of equilibrium. There are 5 such points in the Earth-Sun system, labelled L1 through L5. At these locations, a spacecraft can maintain a stable position relative to both bodies with minimal fuel. The James Webb Space Telescope orbits the L2 point, about 1.5 million kilometers from Earth, where it has an unobstructed view of deep space while remaining relatively close to home. Gravity also explains the synchronous rotation of many moons, including our own. The moon always shows us the same face because its rotation period exactly matches its orbital period around Earth. Both take about 27.3 days. This isn't coincidence. It's called tidal locking. Over billions of years, Earth's gravity created tidal bulges in the moon's rocky body, and the gravitational interaction between Earth and these bulges gradually slowed the moon's rotation until it locked into synchronization. Many moons throughout the solar system are similarly locked to their parent planets. Here's something that affects every human endeavor beyond Earth: the gravity assist maneuver, sometimes called a gravitational slingshot. When a spacecraft flies past a planet, it can use that planet's gravity and orbital motion to change speed and direction without using fuel. The Voyager probes use gravity assists from Jupiter and Saturn to reach the outer solar system and eventually interstellar space. The technique works because momentum and energy are exchanged between the spacecraft and the planet. The spacecraft gains speed while the planet loses an infinitesimally small amount. It's like playing catch with worlds. Let's talk about something that seems impossible but isn't. The gravitational constant might not actually be constant across cosmic time. Some physicists have proposed that G, that fundamental number in Newton's equation, could have been different in the early universe, or might vary slightly in different regions of space. The evidence remains controversial and inconclusive, but the possibility reminds us that even our most fundamental understanding of gravity might still be incomplete. Current measurements show that if G is changing, it's doing so incredibly slowly, less than 1 part in 10 trillion per year. Gravity creates something called a gravitational potential well, a useful way of visualizing how gravity affects space around a massive object. Imagine a deep, curved valley with a massive object at the bottom. The steeper the sides, the stronger the gravity. Earth sits in the Sun's gravitational well, and we sit in Earth's well, which itself sits in the Sun's well. Climbing out of a gravitational well requires energy, which is why launching rockets is so difficult and expensive. About 95% of a rocket's fuel is used just escaping Earth's gravitational well. And here's a fascinating consequence of orbits and gravity. Every planet, moon, and asteroid is constantly falling. Earth is falling around the Sun, the Moon is falling around Earth, and the Sun itself is falling around the center of the Milky Way galaxy. at a speed of about 230 kilometers per second. We're all in perpetual free fall through space, following the curved paths that gravity prescribes, held in an eternal cosmic dance that began billions of years ago and will continue for billions more. As we explore further, we'll discover how gravity shapes not just objects and orbits, but the destiny of the universe itself. Let's consider something both ancient and immediate, the equivalence principle, one of Einstein's most profound insights. He realized that being in a gravitational field is fundamentally indistinguishable from being accelerated. If you were in a closed elevator in deep space accelerating upward at 9.8 meters per second squared, you would feel exactly the same as you do standing on Earth's surface. Drop something and it would fall to the floor just as it does here. This isn't just a similarity. It's a deep truth about the nature of reality that led Einstein to general relativity. Gravity and acceleration are two sides of the same coin. This brings us to gravitational redshift, a phenomenon where light climbing out of a gravitational well loses energy and shifts toward the red end of the spectrum. When light escapes from a massive object, it must work against gravity, and in doing so, its wavelength stretches and its frequency decreases. This has been measured with exquisite precision using atomic clocks at different altitudes. In 2010, scientists detected gravitational redshift between two clocks separated by just 33 centimeters, about 1 foot. Gravity's influence on time and light operates even across the height of a small table. Now, imagine the largest gravitational structures in the universe, galaxy clusters. These are collections of hundreds or even thousands of galaxies, all bound together by gravity. The Coma cluster, for instance, contains over 1,000 galaxies and has a total mass more than a quadrillion times that of our Sun. But here's what's strange. When astronomers calculate how much gravity is needed to hold these clusters together based on the visible matter they contain, the numbers don't add up. There isn't enough visible matter. This observation, first made in the 1930s by Fritz Zwicky, led to one of the greatest mysteries in modern physics. That mystery is dark matter, an invisible form of matter that interacts with ordinary matter only through gravity. Current estimates suggest that dark matter makes up about 27% of the universe's total mass energy content, while the ordinary matter that makes up stars, planets, and everything we can see accounts for only about 5%. We know dark matter exists because we can see its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone, and gravitational lensing reveals mass when nothing luminous appears. Yet dark matter remains invisible to telescopes, passing through ordinary matter like a ghost. Speaking of gravitational lensing, this is one of the most beautiful confirmations of general relativity. When light from a distant galaxy passes near a massive object like a galaxy cluster, the space-time curvature bends that light, acting like a cosmic lens. Sometimes this creates multiple images of the same distant object, or stretches it into arcs and rings. The most extreme examples are called Einstein rings, perfect circles of light formed when a distant galaxy, a massive lensing object, and Earth align precisely. These gravitational telescopes allow us to see objects that would otherwise be too distant and faint to detect. Let's return to Earth for a moment and consider something called the geoid. Earth's gravity isn't uniform. It varies slightly from place to place due to differences in density of the rock below, the presence of mountains and ocean trenches, and the distribution of mass within the planet. The geoid is a model of Earth's shape based solely on gravity and rotation, representing what sea level would be if it could flow through continents. It's lumpy and irregular, with variations of up to 100 meters from a perfect ellipsoid. Satellites like GRACE and GRACE-FO map these gravitational variations with incredible precision, revealing information about water storage, ice sheet loss, and even earthquake-induced changes in Earth's mass distribution. Here's something that connects the very small to the very large: the Schwarzschild radius. For any given mass, there's a critical radius at which, if all that mass were compressed into a sphere of that size, it would become a black hole. This radius is proportional to the object's mass. For our Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it's only about 9 millimeters, as we mentioned earlier. For a human weighing 70 kilograms, the Schwarzschild radius is absurdly tiny, about 10 to the negative 25th meters, far smaller than an atomic nucleus. This calculation shows just how much compression would be required to turn ordinary matter into a black hole. Gravity also governs the Roche limit, the distance within which a celestial body held together only by its own gravity will be torn apart by tidal forces from a larger body. It's named after Edouard Roche, who calculated it in 1848. Saturn's magnificent rings exist because they lie within Saturn's Roche limit. Any moon-sized object that ventures too close to Saturn will be shredded by tidal forces, unable to hold itself together against the gradient in Saturn's gravitational field. The particles in Saturn's rings are the remnants of such unfortunate visitors, or perhaps material that could never coalesce into a moon because it was always inside this forbidden zone. Consider also how gravity affects the shape of large bodies. Objects in space naturally become spherical once they grow massive enough, because gravity pulls equally in all directions toward the center. But there's a size threshold. Bodies smaller than about 600 kilometers in diameter don't have enough gravity to overcome the structural strength of rock and pull themselves into spheres. That's why asteroids tend to be lumpy and irregular, while planets and large moons are round. The transition happens gradually. Ceres, at 940 kilometers across, is nearly spherical, while Vesta, at 525 kilometers, is noticeably irregular despite being large. These principles of gravity, operating across scales from subatomic to cosmic, reveal a universe of exquisite order beneath apparent chaos. Let's explore something that challenges our everyday intuition. Weightlessness isn't the absence of gravity. When astronauts float aboard the International Space Station, Earth's gravity is still pulling them with nearly the same force you feel right now. They appear weightless because they're in free fall, and so is everything around them. Weight is the sensation of something pushing back against gravity's pull. The floor beneath your feet, the chair supporting you. Remove that support and you become weightless, even though gravity remains. Stand on a scale in an elevator that's in free fall, and the scale would read 0, not because gravity disappeared, but because both you and the scale are accelerating downward together. Now consider the three-body problem, one of the oldest puzzles in physics. Newton could perfectly predict the motion of two bodies orbiting each other under gravity's influence. But add just one more body, and the mathematics becomes extraordinarily complex. There's no general solution, no simple formula that predicts exactly where three gravitationally interacting bodies will be at any given time. For most configurations, the system is chaotic, meaning tiny differences in starting conditions lead to vastly different outcomes. This is why predicting the long-term stability of planetary systems, or the precise trajectory of asteroids influenced by multiple planets, requires powerful computers running complex simulations. Gravity also determines what we call hydrostatic equilibrium, the balance between gravity pulling inward and pressure pushing outward. Stars spend most of their lives in this delicate balance. The sun's core is so hot and dense that the outward pressure from nuclear fusion exactly counteracts gravity's inward crush. When a star exhausts its fuel, this equilibrium breaks. If the star is massive enough, gravity wins catastrophically, leading to a supernova explosion or the formation of a neutron star or black hole. Our sun will eventually swell into a red giant when helium fusion begins creating new outward pressure, then finally collapse into a white dwarf when fusion ceases entirely. Here's something remarkable about Jupiter. This giant planet actually protects Earth from some asteroid and comet impacts. Jupiter's immense gravity, about 2.5 times stronger than all the other planets combined, acts like a cosmic vacuum cleaner, capturing or deflecting objects that might otherwise threaten the inner solar system. The famous Shoemaker-Levy 9 comet demonstrated this in 1994, when it broke apart and crashed into Jupiter, leaving impact scars larger than Earth. Some scientists believe that without Jupiter's gravitational influence, life on Earth might never have had the stable environment needed to evolve over billions of years. Let's talk about something called frame dragging, a bizarre prediction of general relativity. Massive rotating objects don't just curve space-time, they twist it. Earth's rotation drags space-time around with it, like honey swirling around a spinning spoon. This effect is tiny but measurable. The Gravity Probe B satellite, launched in 2004, carried gyroscopes so precise they could detect this space-time twisting. After years of data analysis, the results confirmed Einstein's prediction. Earth's rotation does drag space-time, causing the gyroscopes to precess by about 37 milliseconds per year. Reality itself rotates with our planet. Consider the cosmic speed limit that governs all massive objects. The speed of light, approximately 299,792 kilometers per second. No object with mass can reach this speed, no matter how much energy you add. But here's what's fascinating about gravity. Gravitational acceleration isn't limited by this rule in the way you might think. In the immediate vicinity of a black hole's event horizon, objects fall inward at velocities approaching the speed of light. The event horizon itself is defined as the distance where the escape velocity equals light speed. Beyond that boundary, not even light moves fast enough to escape, not because something is pulling it back, but because all possible future paths through space-time lead inward. Now, imagine the early universe, mere moments after the Big Bang. gravity has been shaping the cosmos since those first instants. Tiny quantum fluctuations in density, present when the universe was less than a trillionth of a second old, were amplified by gravity over billions of years into the vast cosmic web we see today. Superclusters, filaments, and vast voids. The cosmic microwave background radiation, that faint afterglow of the Big Bang, shows us the seeds of all future structure. Regions that were slightly denser than average, where gravity would eventually gather matter into galaxies and stars. Every galaxy, every star, every world traces its existence back to gravity, amplifying those primordial ripples. Here's something that connects quantum mechanics and gravity in a mysterious way. The Planck length, approximately 1.6 times 10 to the negative 35th meters. This is the scale at which quantum effects of gravity should become important, where the smooth fabric of space-time described by general relativity should give way to a quantum foam of fluctuating geometry. We have no theory yet that fully describes physics at this scale. General relativity and quantum mechanics, our two most successful theories, become incompatible in this realm. Understanding quantum gravity remains one of the greatest challenges in physics. Finally, consider orbital resonance, a gravitational phenomenon that creates beautiful patterns throughout the solar system. When two orbiting bodies exert regular, periodic gravitational influences on each other, their orbital periods can become locked in simple integer ratios. Jupiter's moons, Io, Europa, and Ganymede are locked in a 1 to 2 to 4 resonance. For every orbit Ganymede completes, Europa completes 2 and Io completes 4. These gravitational tugs keep Io's orbit slightly elliptical, causing tidal heating that powers the most volcanically active world in our solar system. Even Neptune and Pluto are in a 3 to 2 resonance, ensuring they never collide despite their orbital paths crossing when viewed from above. As we continue deeper into gravity's mysteries, we'll discover how this force not only shapes the present, but will determine the ultimate fate of everything that exists. Let's contemplate neutron stars, some of the most extreme objects in the universe. When a massive star explodes in a supernova, its core can collapse into a sphere only about 20 kilometers across, yet containing more mass than our entire sun. The gravity is so intense that protons and electrons are crushed together to form neutrons, creating matter at densities comparable to an atomic nucleus. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. The surface gravity is approximately 200 billion times stronger than Earth's. If you somehow stood on a neutron star, you would be flattened to less than 1 millimeter thick, and any attempt to stand would result in your atoms being compressed beyond recognition. Some neutron stars spin with incredible speed, hundreds of times per second, while emitting beams of radiation from their magnetic poles. We call these pulsars, and they're among the most precise clocks in the universe. The fastest known pulsar, PSRJ 1748-2446 AD, rotates 716 times per second. Its equator is moving at about 24% the speed of light. These objects maintain such rapid rotation because of conservation of angular momentum. As the star's core collapses, it spins faster, like a figure skater pulling in their arms. Their gravity is so strong and their density so uniform that they keep this spin for millions of years with barely any slowdown. Now, let's explore something called the Hill sphere, also known as the Roche sphere, the region around a planet where its gravity dominates over the Sun's gravity. For Earth, this sphere extends about 1.5 million kilometers. The Moon orbits well within Earth's Hill sphere, at only about 384,000 kilometers away, which is why it orbits us rather than the Sun. Every planet has such a sphere, and objects within it are gravitationally bound to that planet. Jupiter's Hill sphere is enormous, extending about 53 million kilometers, which explains why it can hold on to so many moons. At least 95 confirmed at last count. Here's a gravitational effect you've experienced without realizing it, the Coriolis effect. While not directly caused by gravity, it works in concert with it. Earth's rotation means that different latitudes move at different speeds. The equator travels faster than the poles because it has farther to go in each rotation. When air or water moves across latitudes, this speed difference causes apparent deflection. Combined with gravity holding the atmosphere and oceans to Earth's surface, the Coriolis effect shapes weather patterns, creates the spiral structure of hurricanes, and even affects the trajectory of long-range artillery. It's gravity and rotation working together to choreograph the motion of fluids on our spinning world. Consider the remarkable precision required for gravitational experiments. The original Cavendish experiment in 1798, which first measured the gravitational constant G, used a torsion balance so sensitive it could detect the gravitational attraction between lead spheres weighing about 158 kilograms and much smaller spheres of about 0.73 kilograms. The apparatus had to be isolated from air currents, temperature changes, and vibrations. Even the gravitational pull of nearby mountains affected the measurements. Modern experiments to measure G are even more demanding. Variations in groundwater levels, atmospheric pressure, and even the position of the moon can introduce errors if not carefully accounted for. Let's talk about something that sounds like science fiction but is real: gravitational time travel. Not traveling backward in time, but traveling forward faster than you otherwise would. The stronger the gravity, the slower time passes relative to weaker gravitational fields. If you orbited close to a black hole's event horizon for what felt like a few hours to you, thousands or even millions of years could pass in the universe beyond. This isn't theoretical speculation. It's a mathematical certainty of general relativity. You would return to find civilizations risen and fallen, continents reshaped, the night sky transformed. Gravity offers a one-way ticket to the far future. Here's something elegant about planetary formation. Gravity doesn't just pull matter together randomly. It creates structure through a process called gravitational collapse. A cloud of gas and dust begins to collapse under its own gravity. As it collapses, it spins faster, flattening into a disk. The center becomes dense and hot enough to ignite as a star, while material in the disk gradually clumps together through gravitational attraction, growing from dust to pebbles, to boulders, to planetesimals, to protoplanets, to planets. This is why planets orbit in roughly the same plane and in the same direction. They inherited their motion from the original rotating disk. Gravity is the sculptor, but rotation and angular momentum guide the chisel. Now consider something called gravitational potential energy. When you lift an object against gravity, you're storing energy in the gravitational field. Drop it, and that stored energy converts to kinetic energy, the energy of motion. This principle powers hydroelectric dams, governs avalanches, and explains why a boulder perched on a mountain represents potential danger. On cosmic scales, gravitational potential energy is staggering. When matter falls into a black hole, it can release more energy than nuclear fusion. The brightest sustained sources of light in the universe, quasars, are powered by matter spiraling into supermassive black holes, converting gravitational potential energy into radiation so intense it outshines entire galaxies. Finally, let's contemplate gravitational waves once more, but from a different angle. These ripples in space-time travel at the speed of light and carry energy away from their source. When LIGO detected those first gravitational waves from merging black holes, the peak power output of that collision, for a brief fraction of a second, exceeded the combined light output of all the stars in the observable universe. Yet by the time those waves reached Earth, after traveling 1.3 billion years, they stretched and squeezed space by less than 1,000th the width of a proton. LIGO detected this impossibly tiny distortion, opening an entirely new way of observing the universe. Not through light, but through gravity itself. These profound truths about gravity reveal a universe far stranger and more wonderful than our ancestors could have imagined, yet governed by principles we can measure, predict, and understand. Let's explore one of the universe's greatest mysteries, dark energy. While dark matter exerts gravitational attraction, dark energy does something that seems impossible. It causes the expansion of the universe to accelerate. Discovered in 1998 through observations of distant supernova, dark energy appears to make up about 68% of the universe's total mass energy content. It acts like a kind of anti-gravity on the largest scales. Though it's not actually repulsive gravity, it's something far stranger. The farther apart objects are, the faster they're pushed apart by dark energy. This means that distant galaxies are receding from us at ever-increasing speeds, and eventually they'll move away faster than light can travel through space, disappearing beyond a cosmic horizon we'll never be able to cross. Consider now the concept of gravitational binding energy, the amount of energy required to completely disassemble an object against its own gravity. For Earth, this energy is about 2.5 times 10 to the 32nd power joules, roughly the amount of energy the Sun produces in an entire week. This is why planets don't spontaneously fly apart, and why it would take an unimaginable catastrophe to destroy one. The Death Star's planet-destroying capability in Star Wars isn't just impressive. It's a demonstration of energy on a scale that dwarfs our current technology by factors we struggle to comprehend. Let's turn our attention to something called the equivalence of mass and energy, Einstein's famous E equals mcc squared. This equation has profound implications for gravity. Mass and energy are interchangeable, and since gravity responds to mass, it also responds to energy. Even massless photons of light are affected by gravity and create their own tiny gravitational fields. A beam of light has weight in a sense, not because photons have mass, but because their energy is equivalent to mass. This is part of why black holes can trap light. The intense gravitational field responds to light's energy, bending space-time so severely that no path leads outward. Here's something that reveals the universe's timeline. Gravitational waves travel at the speed of light, which means they bring us information from the distant past. When LIGO detected those merging black holes, it wasn't seeing them as they are now. It was witnessing an event that occurred 1.3 billion years ago, when life on Earth consisted only of simple single-celled organisms. Gravitational wave astronomy lets us watch the universe's violent past unfold, collision by collision, across billions of years. Some detected mergers happened so long ago that the galaxies hosting them may no longer exist in any recognizable form. Now consider something closer to home. Precession. Earth's axis doesn't point in a fixed direction. It slowly wobbles like a spinning top, completing one full circle about every 26,000 years. This precession is caused by gravitational torque from the Sun and Moon acting on Earth's equatorial bulge. Right now, Earth's axis points roughly toward Polaris, our North Star, but in about 13,000 years, it will point toward the star Vega instead. Ancient Egyptians who built the pyramids saw different pole stars than we do. Gravity's influence extends even to the orientation of worlds, gradually shifting the celestial scenery over millennia. Let's discuss something profound: the cosmic microwave background and what it tells us about gravity's role in the early universe. When the universe was only about 380,000 years old, it had cooled enough for atoms to form and light to travel freely. The cosmic microwave background is that light, now stretched by cosmic expansion into microwave wavelengths. Its temperature varies by only about 1 part in 100,000 across the sky. But those tiny variations represent regions of slightly different density. Gravity has been working on those density differences ever since, pulling matter together over billions of years. The hot and cold spots in the cosmic microwave background are essentially a baby picture of all future galaxies, clusters, and cosmic structure. Here's something that demonstrates gravity's strength despite being the weakest force. Gravitational waves from merging black holes carry away tremendous energy. In the first detected merger, about 3 solar masses worth of energy, the equivalent of 3 entire suns converted completely to pure energy via E equals mc squared, was radiated away as gravitational waves in less than a second. This energy didn't vanish. It rippled through space-time itself, carrying information about the collision to observers billions of light years away. The fabric of space itself became the medium for transmitting this cosmic signal. Consider the fascinating case of binary pulsars, pairs of neutron stars orbiting each other. In 1974, astronomers discovered PSRB 1913 plus 16, the first binary pulsar system. Over decades of observation, they noticed that the orbital period was gradually decreasing. The 2 neutron stars were spiraling closer together. The energy being lost matched exactly Einstein's prediction for gravitational wave emission. This was the first indirect evidence for gravitational waves, years before LIGO would detect them directly. Russell Hall's and Joseph Taylor won the Nobel Prize for this discovery, which proved that gravitational waves aren't just theoretical, they're real phenomena carrying energy across the cosmos. Let's explore something called the stress energy tensor, a mathematical object in general relativity that describes all forms of energy and momentum in space-time. This tensor is what curves space-time, not just mass, but all energy, pressure, momentum, and stress. Even the tension in a stretched rope contributes infinitesimally to space-time curvature. The right side of Einstein's field equations contains this tensor, representing all possible sources of gravity. The left side describes the curvature of space-time itself. The equations state that matter and energy tell space-time how to curve, and curved space-time tells matter and energy how to move. It's a conversation between substance and geometry, forever ongoing. These layers of understanding, built over centuries of observation and thought, show us that gravity is far more than a simple force. It's a fundamental feature of reality, woven into the fabric of existence itself, shaping everything from the fall of an apple to the destiny of the cosmos. As we approach the end of this journey through gravity's wonders, let's contemplate the ultimate fate of the universe itself. Cosmologists have identified several possible scenarios, all determined by the interplay between gravity and dark energy. If gravity eventually overcomes cosmic expansion, the universe could collapse in a big crunch, everything rushing back together in a reverse of the Big Bang. If dark energy continues to dominate, we face a big freeze where galaxies drift ever farther apart, stars exhaust their fuel, and the universe grows dark and cold over trillions upon trillions of years. A third possibility, the Big Rip, would occur if dark energy strengthens over time, eventually tearing apart galaxies, then stars, then planets, then atoms themselves. Current evidence suggests the Big Freeze is most likely, but the universe still holds secrets we haven't yet uncovered. Let's consider the elegant concept of geodesics, the straightest possible paths through curved space-time. When you drop a ball, it's actually following a geodesic, moving in a straight line through the curved geometry around Earth. Planets orbit the Sun along geodesics, and light from distant stars travels along geodesics that are bent by massive objects. Nothing is being pulled or pushed. Objects simply follow the natural geometry of space-time. This is the profound beauty of general relativity. Motion under gravity isn't caused by a force, but by the shape of reality itself. A planet doesn't know the Sun is there. It simply follows the curved path beneath it. Here's something that bridges the quantum and cosmic realms: Hawking radiation. In 1974, Stephen Hawking discovered that black holes aren't perfectly black. They emit a faint glow of particles due to quantum effects near the event horizon. Virtual particle pairs constantly pop into existence throughout space, normally annihilating immediately. But near a black hole's event horizon, one particle can fall in while the other escapes. To an outside observer, the black hole appears to emit radiation. This radiation is incredibly faint. A solar mass black hole would have a temperature of only about 60 billionths of a degree above absolute zero. But given enough time, far longer than the current age of the universe, even black holes will evaporate completely, returning their mass to the cosmos as radiation. Consider the remarkable precision of gravitational measurements in testing general relativity. The Cassini spacecraft, while passing behind the Sun as seen from Earth, allowed scientists to measure how radio signals were delayed by the Sun's gravitational field. The measurement matched Einstein's predictions to within 0.002%, an extraordinary confirmation of general relativity's accuracy. Similarly, observations of Mercury's orbit showed that its perihelion, the point of closest approach to the Sun, precesses by 43 arcseconds per century more than Newton's laws predicted. General relativity explained this discrepancy perfectly, accounting for the curvature of space-time near the Sun. Let's talk about something that reveals gravity's quantum nature. Attempts to detect gravitons, the hypothetical particles that would carry the gravitational force. Just as photons carry the electromagnetic force, gravitons would be the quantum messengers of gravity. But detecting a single graviton would require a detector with the mass of Jupiter orbiting a neutron star, a practical impossibility. Gravitons, if they exist, interact so weakly with matter that they pass through everything essentially undetected. This illustrates why unifying quantum mechanics and gravity remains so challenging. Gravity is extraordinarily weak at quantum scales, making its quantum effects nearly impossible to observe directly. Now consider gravitational microlensing, a technique that has revolutionized the search for exoplanets and dark matter. When a foreground object passes in front of a distant star, its gravity bends the star's light, causing a brief brightening that can last hours to months. If the foreground object is a star with planets, those planets create additional spikes in the brightness curve. This method can detect planets far too distant and dim to see directly, even planets that don't orbit stars at all. Rogue worlds drifting alone through interstellar space. Gravity becomes a cosmic magnifying glass, revealing invisible worlds through pure geometry. Here's something profound about the nature of gravitational attraction. It violates no conservation laws because the gravitational field itself carries negative energy. When two objects attract and fall together, they gain kinetic energy, but this is balanced by the negative potential energy of the gravitational field between them. The total energy remains constant. This is part of a deeper principle. You can't shield against gravity or create anti-gravity, because doing so would violate energy conservation. Gravity always attracts, always reaches across space, and always must be accounted for in the cosmic ledger. Let's contemplate the gravitational constant's role in the anthropic principle, the observation that the universe seems fine-tuned for life. If G were just slightly larger, stars would burn through their fuel too quickly for complex life to evolve. If it was slightly smaller, stars might never ignite at all, leaving a cold, dark universe. The value of G, along with other fundamental constants, falls within a narrow range that permits the existence of stable stars, planets, and ultimately observers like us to wonder at it all. Whether this is coincidence, necessity, or evidence of a multiverse where different regions have different constants remains one of philosophy's and cosmology's deepest questions. Finally, let's return to where we began, to you, sitting or standing, feeling gravity's gentle but insistent pull. Every breath you take, every heartbeat happens within gravity's embrace. The weight you feel is your connection to the entire mass of Earth, pulling you toward its center with the same universal force that holds galaxies together and guides planets in their orbits. You are part of this cosmic dance, a collection of atoms that once drifted through space, brought together by gravity into the miraculous complexity of a living, thinking being. From the smallest quantum fluctuations to the largest structures in the cosmos, from the first moments after the Big Bang to the distant future trillions of years hence, gravity shapes everything. It is patient and persistent, weak yet inexorable, simple in concept yet infinite in consequence. And now, having explored these 100 facets of gravity's nature, perhaps you'll feel its pull a little differently, not as a burden holding you down, but as a profound connection to everything that exists, has existed, or ever will exist in this magnificent universe we call home. Thank you for joining me on this journey through the mysteries of gravity. May you carry these wonders with you, and may they inspire you to look at the ordinary world with extraordinary eyes.